Welcome to TaiyangNews and SNEC Solar Leadership Conversations. I am Shravan K.Chunduri, Head of Technology at TaiyangNews, all about solar. We are happy to have with us father of photovoltaics, the modern PV, Martin Green from UNSW. He is actually the mastermind behind many technologies that have shaped the solar industry today. For example, PERC and TOPCon are the names that have really came into the mainstream. And we are very glad to have Martin. Welcome, Martin.
Thank you.
So, Martin, just reflecting a little bit back, there were several innovations that have happened last year, and it is very difficult to keep a track of them. So maybe you can help us and tell us what you thought were the three major technological developments from your point of view.
Yeah, like there had been many, and like you say, it's been hard to keep track of them. But yeah, I think Longi setting new world records, initially with heterojunction cells, and then with their version of IBC cells. I guess it's a HBC cell. That's obviously got to be a highlight because they're making real progress in improving the efficiency limits towards the ultimate capability. So that was great to see. Also commercially, it was interesting to see the introduction of all back contact cells and so on onto the market with such a sort of substantial efficiency performance gain over the competing products. So I think that sort of pointed the way to the future to me. I think everyone's going to have to go to all back contacts or equivalent technology down the track. And I guess again progress with the perovskite silicon tandems has been encouraging in the way everything keeps going up, but what I'm missing there is reports of module durability and so on. It's plenty of excitement about incremental improvements in efficiency and so on, but very little information that I can find about how the module durability is improving.
Okay. So what are the most important topics you are working at UNSW to bring the solar to the next level, and what is also it?
Yeah, we've been working a long time on silicon tandems, and so including perovskite silicon tandems, but most of the effort is being focused on the perovskite silicon tandems, and my concern there is it might be that perovskites never proved to have the required stability to introduce a commercial product in that area. So we've been looking at other alternatives. So, for example, we hold the world record with the pure sulfide CZTS technology, and we're making, incremental gains with efficiency, although, to use in a tandem, you have to be above 20%, and we're above 12% now, but we've still got a long way to go to get to 20%. And then we're working with other technologies that are less well known for as possible tandems to stack onto silicon, because obviously that's the way the industry needs to go if you can find a material that's stable enough and cheap enough to use in that application.
Okay. The technology landscape today is quite different from what it used to be in the past. So in the past, we had only one technology in the main commercial production, and there is one technology which is under research. But today, we have, of course, TOPCon as the mainstream, but we also have heterojunction and IBC in mass production, though in very less quantities in terms of capacities. So how do you see this diversification of the technologies impacting the photovoltaic industry, and what are the potential benefits and also the shortcomings associated this multi-technology approach right now in the industry?
Yeah, no, as you say, like I think it was the success of the introduction of PERC has made the whole industry a lot more adventurous in adopting new technology. So, when you look back on it, the PERC introduction was a huge success and really opened up the gates to a lot of new technology, in the module area as well as in the cell area. I think ultimately it's all about efficiency. So, processing complexity and so on is something that eventually companies will find a way of getting under control. And so it's ultimately about efficiency. And surprisingly, I think it determines about, it's determined by the voltage capability of the technology. So with heterojunctions now, they've shown, like Longi have shown they can get what are they getting? Over 770 millivolts on thin heterojunction cells now. And that has a surprising effect of leading to higher fill factors, because once you start getting the open circuit voltage constrained by Auger recombination, which is happening in their cells now, you can capture some of that. This benefit has an improved fill factor. So to me, the battle between TOPCon and heterojunction depends on whether TOPCon can reach the same voltages that we're seeing with heterojunctions. Or maybe it's a hybrid technology like Goldstone have pioneered, where you use the P-type heterojunction and the N-type TOPCon, maybe something like that. But it's all about voltage, in the end, I think. So my own view is that the introduction of tandem cells is going to be delayed. So we'll see the single silicon cell technology get pushed right to its limits in terms of performance. And that'll require getting the fill factor boost that you get from ultra high voltages.
Okay. So, talking a little bit specific to each technology, like TOPCon, heterojunction, and IBC. So where are they right now in your view, and what can be done? So what are the possible improvements or the potential these technologies offering to go to the next level?
Yeah, so I think it's all about fill factor. So, with the heterojunctions now, like companies like Longi and SunDrive have shown they can get into this regime of enhanced fill factors. Like there's a lot of enhanced fill factors being reported in the literature and from various measurement centers, but often they're just mismeasurements. But there is the potential for getting real enhancements in fill factor once you get into the Auger limited regime of operation. So, like the heterojunctions have shown they're already there, and I think with ongoing improvements, they'll comfortably exist in that area. So that might give them a fundamental advantage. Like it's about a 4% relative advantage from this fill factor boost. So if you can't get into that regime where TOPCon isn't there yet, if TOPCon can't battle its way into that regime, there's going to be a 4% differential between the technologies, which is probably large enough to drive the commercialization of heterojunctions relative to TOPCon. And then again, there's the hybrid, like Goldstone have demonstrated the hybrid, combining the best of the TOPCon with the best of the heterojunction. So that's another option there. But it's all about fill factor ultimately, I think.
Okay. So talking a little bit about the perovskite tandems, the major chunk of the industry is working on a cell level tandem, but companies like GCL, perovskite Wing, they're trying to do the module level tandem. So in your view, what's the best approach?
I think there's a fundamental problem with the module level in that, like thin film modules, like if you look at First Solar Modules, who's the most successful thin film company, they're operating at hundreds of volts. And then if you look at the silicon companies, they're operating at much lower voltages. So to me, you can't continue having independent wiring right through the field. You have to close things off at the module level. So very difficult to do with a combination of perovskite, thin film, and silicon. Whereas stacking the perovskite cell directly onto the silicon and making contact at the cell level, is an easier way around it. And to me, it just seems that the production costs are going to be lower because the silicon cell manufacturing industry has shown the ability to really take the cost out of converting wafers into operational cells. No matter how complex the technology, they've always been able to do it cheaply in the long run.
So, looking at the recent developments in the perovskite segment, just you mentioned, there were a couple of record tandem cells. And so when do you think the technology will hit the commercialization point? Just looking in the crystal ball.
Yeah, well, there's some companies already testing the water, but when it will hit the commercialization point successfully, I think it depends upon the durability of the product. And there's very little in the literature to give you confidence that you're looking at more than, say, a year durability for a product that's at the level that you'd need it to be performing to compete on the market. So, you can hide the degradation of perovskite cells by starting off at very low levels, and they may be deteriorating, but you just don't see it because something else is limiting their performance. But if you're looking at high performance product, there's very little evidence to show that you could get more than a year's life out of that product in the field, which it's not enough. If you still go by the present standards of 20% degradation being end of life.
In the past, you argued that it is very important to have, cost per square meter rather than cost per watt. There is also an interesting article, and that was really going viral on social media that, the balcony, the fencing systems built with solar are much cost effective compared to the regular, the traditional material, using traditional materials. So, has the time has arrived for solar to become a true building integrated material with this low cost, what we are seeing right now?
Yeah, I guess building integration hasn't had a happy history in photovoltaics. So it seems like something that should be a natural match, but even Elon Musk couldn't make it work. He's made many impossible technologies work, but he couldn't make solar roof tiles, turn that into a viable product, even though it was obviously a very attractive product and had the full strength of his marketing expertise behind it. So it's been a very difficult area. So, I think, architects like doing things custom, and that's not conducive to low cost with photovoltaics, I think is, one of the basic problems.
So what are the major bottlenecks here? So is it really changing the mindset, or what is the key bottleneck here for PV really getting into the building material?
Yeah, I'm not sure. So we were very enthusiastic about building integrated photovoltaics in the 90s, when photovoltaic wasn't competitive in many applications, but we figure when people were paying, hundreds of dollars a square meter for marble building faces and everything, if you could have a photovoltaic one that was also doing something useful, you might be able to establish it as an architectural trend or something like that, but it never really caught on. But I'm not sure, maybe putting more effort into establishing the idea of photovoltaics within the architectural field might be one way of going, maybe competitions to show, really exciting uses of photovoltaics in buildings or something like that might be what you need to trigger it off. So, like in the 90s, I teamed up with one of Australia's best-known architects, Harry Seidler. He was interested in building integrated photovoltaics, mainly because a lot of his buildings were controversial in their location, but by adding this environmental element to it, he had a way of selling these projects that would otherwise be difficult. But, we didn't have any luck in pulling that off. But my hope was we could make it some type of architectural trend, which hasn't really happened.
So, what is the next solar technology in your view? Because right now, whenever we were discussing about one mainstream technology, we had next level. So, I think tandem is kind of approachable. It's not yet there, but I think we can see that. So, what is the next? Is it several tandems, or how future technology would look like?
Yeah, so like I don't see tandems being quite as close as you might, but so I think once you can find a material that you can stack onto silicon, and I think you need to stack it onto silicon first just to take advantage of the marketing and sales and resources of the companies that are involved in the industry. The first cell you have to change the metallization approaches. You need transparent conducting oxides and things, more like thin film technology to do the contacting. But your second cell you sort of get for free. It just sort of slots in between the top cell and the middle one. Okay. So you can stack two cells onto silicon, but every time you stack a cell onto silicon, you reduce the power contribution of the silicon cell to the total power. So by the time you get to a 3-cell stack, you're only getting a third the power from the silicon you'd get by itself. So for a 4-cell stack, you might say, by this stage, the cells that you're stacking on top of silicon would have had terawatts of exposure in the field and so on. So you'd be fairly confident about their ability to stand by themselves. So I think a 4-cell stack might be all thin film. So that's my prognosis. So whatever technology we can find that stacks onto silicon, and it still could be perovskites, but there's a few challenges in the way, I think. You could just sort of see going to a 2-cell stack on silicon as a no-brainer, and then maybe the transition to all thin film there. And then we can see how manufacturers like to have a small competitive edge over their competitors. So stacking 5 cells, 6 cells, you're diminishing returns with each cell, but you would get that little bit in front of your competitors. So you might just keep stacking cells up to a dozen cells on top of one another, just to have the marketing advantage of slightly higher performance.
Great. Thank you very much, Martin. Thanks. Okay.
Well, thank you. Good talking to you.
Very, very nice.